In 1943, in Lund, Sweden, after arduous process of investigation and development, and as an answer to the needs in the field of food storage arising from the multiple industrial processes entered by the man from the 20th century, it is born the container Long Life. Nevertheless, it continues being perfected until the levels we know nowadays. Long Life container is made out of aluminium. It protects the product of external agents, scents, flavors, light. Polythene of low density. It makes the package waterproof, protects the product, and it provides strapping to it. Pulp of paper. Give the physical structure to the package. Gives its shape to keep it firm. This wonderful formula for the package of liquids and semi-liquids, and whose revolutionary versatility allows infinity of utilities worldwide in the nutritional sector, has become, throughout the last 50 years, the best tool for the food storage without needing refrigeration whatsoever. Kindness and benefits of Long Life containers are practically in all the markets of the world, solving the diverse problems of refrigeration, preservation, and transport that affect the postmodern society. Its growth throughout each corner of the planet has arrived at such level that today takes place 300,000 containers per minute in more than the 45 factories around the world. However, as it happens to a great amount of inventions and industrial developments of our days, they themselves generate other complications for the planet that often take us to think if the solution is being more serious than the original problem. Long Life container is not the exception to this question. Due to its elements and the pressing applied to it, its biodegradability is practically impossible. Although the Long Life container has originally solved a question for the humanity in a not long run, it is perhaps creating a more complex one. In 1950, 75.9 tons of packing took place. For the 2005, 2.2 million tons of packing, and for 2015, it is calculated that around 30 million tons of packing. Let's see the comparative picture now. Year 0, Long Life container intact, baby being born. Year 10, Long Life container intact, playing girl. Year 20, Long Life container intact, youngster in the university. Year 30, Long Life container intact, adult having a son. Year 60, Long Life container intact, adult being grandparent. Year 80, Long Life container intact, adult dying. Year 100, Long Life container intact after 10 generations. Year 300, Long Life container intact, 30 generations have died. Our home has ignited all the possible alerts: the global warming, the frequent floods, defrosting, and avalanches. That is nothing but an alert of the Mother Earth. If it is not listened, will be the end of the world, even before we could imagine. That's why the governments and the private companies from a great number of industrialized countries and others in development have stepped up wisely in an ecological era through the forceful demand in recycling for almost all the industrial and productive processes. The technology of Long Life containers is not outside this urgent planetary necessity, and although many companies have invested hundreds of millions of dollars in investigation and development with the purpose of separating the layers of the packages, this long reality would seem to be the condemned to a way without exit. Nevertheless, after several years of work and a great human and economic effort, a talented group of Colombian professionals has developed a biochemical process for separation and later recovery of the layers that compose all the long-life containers. With such efficiency and simplicity, this technological innovation will revolutionize, without a doubt, the scientific world of the 21st century. This process is called Recopack. Let's see its skillful functioning. A test of removal of the package for foods has begun, made by important multinational companies. In the first beaker, we pour the solution TBA1 or Starty. The package is introduced when solution TBA1 reaches the necessary temperature after the reaction. The layer of the package is introduced and in 5 minutes it is separated. Before the first minute solution TBA1 has reacted in the different layers, we see how the external layer of the low-density package, along with the chemical pulp of paper, have been separated perfectly and totally from the rest of the components of the long-life container. In the second beaker, we pour the TBA2 or homogenization solution in where all the materials finish preparing themselves for the later selection. After the 3 first minutes, we can see how the long-density polythene falls off due to the contact with the solution TBA1, as it happened to the 2 previous layers. 5 minutes have been timed up, and the remaining material is introduced in solution TBA2 with the other materials for an approximately 1 minute. This layer is of low-density polythene. It is the most inner layer of the container. The following one also is of low-density polythene. It is where they print the marks and logos of the companies that use the package. What we see is the chemical pulp of paper of long fiber length. This is the aluminium with a 99% of purity, and that gives the characteristic of aseptic to the package. The mechanical pulp of paper is taking off, and also the long fiber length. And the last, low-density polythene. The order from inner to outer. Low-density polythene, aluminium. Low-density polythene, mechanical pulp of paper, chemical pulp of paper, and low-density polythene. All this process is done easily with handling solutions that do not represent any risk for the atmosphere. The process can be generated to great volumes without any type of technical restrictions. These takes to solve the problem of the recycling of long-life containers in any corner of the world, and it allows its industrialization and commercialization, reaching the best levels of productivity after the investors. Let's analyze this industrial assembly. The process initiates with the displacement of long-life container post-consume through a transporting tape to a mechanical system of rolling punctures that receive the packages and puncture holes on them to facilitate the action of the biochemical substance. This material is given by the tape to a cut station in H that through a single movement with special blades allows to leave the material ready for the following station. At the same time, with the support of a transporting tape, strips of post-material industry are moved through a transporting tape to a mechanical system of rolling punctures that receive the strips and punctures them to expedite the action of biochemical substance. The post-consume materials and post-industry are received by a tape of linked buckets that is submerged in a stainless steel tank, with TBA1 where long-life containers are broken down. The broken down and humid material is given by the tape of linked buckets to a wiring roller system, and by applying moderate pressure, substance is extracted and recovered. The material is received by a tape of link buckets that introduces it in a tank with substance TBA2. Again, through a wiring roller system and by applying moderate pressure, substance is extracted and recovered. Afterwards, the material is given to a centrifuge system where once extracted, the graded amount of humidity of vasculate form it is given by a transporting tape to a drying system and selection of materials that consist of two concentric cylinders of adjustable inclination, which they allowed through a superior duct to select the light materials, plastic and aluminum, to be put in a classification table, and the heavy equipments, paper and cardboard, by gravity, go through a classification board. Once the materials are classified, we proceed to press them and to pack for its later commercialization. As we have seen, we are before a unique opportunity with the planet and the society that we cannot fail to take advantage of. Welcome to the 21st century, to a solution of the 22nd century.